so today we'll do sort of, randomized algorithms part 2. Today will be a little slower because the algorithm is somewhat much more magical, okay? As if randomized quicksort wasn't. So this is a result of, this is known as Karger's Mincut algorithm. And it's a very surprising use of randomized algorithms. So let me first explain what the Mincut problem is. So you have a graph G, V, E, and let's just think of this as, it's a simple undirected graph. Okay, so it's sort of the usual vanilla graph that you think of. This is your graph. So a cut of the graph is basically a partition of the vertices into two sets, S and S complement. That's a cut. So you're basically cutting the graph into two parts, and the cut value is the number of edges between. Okay, so if you have a set S, then you think of S complement, the pair is a cut, or technically the edges that go from S to S complement are the cut edges, or I should say are cut edges. Does that make sense? So you're basically trying to sort of break the graph into two parts. And the min cut is sort of the cut where the minimum edges are cut. It's very simple, right? So we'll say the min cut of the graph is a minimum over all non-zero subsets, right? So you will have every non-trivial cut of the number of edges that go from S to S complement. I'm just using this for the cardinality of that set, right? And this is the number of edges that are going from S to S complement. Does that make sense? So the algorithmic problem is you're given a graph and you want to find the min cut. The min cut value, and you want to actually find an SS complement that give you that cut. Okay, so let's just think about what min cut means. When is the min cut 0? What does it mean for the min cut to be 0? Yeah?
You don't cut the graph?
No, you are cutting the graph, but when is the value 0? Yeah?
Is it when S is the entire graph?
No, okay, so I should say that this less than that, good, right? So I want a non-trivial cut. You're not allowed to, S cannot be empty or everything. So when can the cut value be 0? Like, what does it mean? It means something. Yeah?
They weren't connected in the first place?
Good, so they weren't connected in the first place, meaning that if your graph has more than one connected component, then the cut value is 0, right? Because you actually have a set. So if G has more than one connected component, then the min cut of G is 0, right? Because if you have a graph and this is a connected component, so actually your graph looks something like this, there are no edges in between, so the min cut value is 0. And actually, if you think of it, it's if and only if. G has more than one connected component if and only if the min cut value is 0. Right? So I could remove this and put my double arrow sign there. Does that make sense? That's the min-cut value, right? So I mean, that's what it means to have a min-cut of 0. So there is a linear time algorithm that tells you if the min-cut is 0. BFS, DFS, whatever. Now let me write something else. The min-cut, so for all vertices V, the min-cut is at most the degree of V. Do you see why that's the case? Yeah? Because this is actually a specific cut. One of the cuts is simply take one vertex out, keep everything else, the cut value is the degree. Right? So if you take any one vertex and you make that S, so let's say S is equal to V, and this is S complement, then the cut value is just the degree. Yeah? So I'm just going to write this up. I'm going to keep that over there. Is this clear? Yeah.
So the degree being how many connections?
Yes, the degree is the number of connections. Yeah. So actually, stop me if I say some graph theoretic thing that you haven't heard. Yeah. Okay. So degree is the number of connections. So you're given a graph and you basically want to find a way of cutting it into two parts, minimizing the number of edges in between. Min-cut. Okay. Okay. And for the sake of this algorithm and for the sake of this talk, and also to some extent for the sake of this problem, the min-cut problem is only interesting when the degrees are mostly large. Because if there's a small degree vertex, then that's, usually that's a small cut. The example, or sort of the thing that I want you to have in mind is where m, which is the number of edges. Think of that as something like, some kind of theta n squared. So it's a dense graph, right? So you have a graph where most of the degrees might be like n, right? You have a graph where most of these are probably connected to many other things, but you have this like little bottleneck, and then there are a bunch of things that are all connected to each other. Here, you're trying to find this sort of bottleneck. So min-cut problems are very interesting, for this exact reason. Usually it's you can think of it for sort of devious reasons, which is, let's say you had some sort of computer network. And your min-cut is where if you lost those connections, your computer network gets disconnected. So an adversary targeting a network will try to find the min-cut. Or turn it around, if you're administrating the network, you want to know where the min-cuts are, maybe to protect those. And there's actually an old technical report, I don't know whether it's from Soviet Russia or the CIA, where actually they were saying, look at the rail network of the Soviet Union and find the min-cut. Because those are the things you want to target if you want to separate things. So a lot of optimization actually goes back to World War II and the Cold War, and in general, problems where you have some kind of network, you're trying to break it into two parts, and you want to see what is the minimum number of connections that need to be broken. And the flip side again is if you want to protect your network, you'd like to know where the min-cuts are. Right, so this sort of, how many of you remember, this was maybe a few years ago, like a significant portion of New York lost power. New York, or I think like part of the Northeast. It was basically a min-cut issue. What happened was there was a particular failure, or a tree went down on a few lines, and that lines just disconnected the whole power network. So again, the problem was you have a power network with a small min-cut value, right? So min-cut type problems come up a lot in these contexts. Okay, and so the question is, you want to actually find the algorithmic problem is how do you find the min-cut? How many of you have taken 102? Some of you only. Okay. So for those of you who have taken 102, you would have seen a min-cut algorithm. Maybe not in that form, but so what? Yeah, what did you see? how do you find a min-cut? Yeah?
Do you use prims? No,
That's spanning trees. Okay, if most of you haven't taken one, do you have your hand up? No. No. If most of you haven't taken one or two, maybe it's superfluous. But there's something called the Maxwell min-cut theorem, and which is a fairly challenging, difficult theorem. You can use the Maxwell min-cut theorem on all different pairs or many different pairs, and you can use that to find the min-cut. It's a fairly complicated algorithm. It would take you about 2 lectures at least to kind of learn what's going on. And what Karger came up with was this incredibly simple min-cut algorithm that uses randomization. Okay? All right.
What's the runtime-ish of, in addition to being really complicated, what would be the runtime?
Yeah, so I think that, you should think of it as how many flow computations do you need to do?
Right.
So you probably need,
and do O of n.
Yeah, the thing is, it's not even, sorry?
Do you have to do O of n squared flow computations?
No, you can do O of n because you can say is for every source, you just have to choose every other destination. You don't have to do all pairs, so you save an extra factor there. But what is incredible about Karger's min-cut, the obvious algorithm is more expensive, but Karger has a way of tweaking it so that your runtime is basically just this. It's just O of n, it's just n squared log n, right? And it's an incredibly simple algorithm. Okay, so do you understand what the min-cut problem is? Okay, so I'll get rid of this picture, and I will get rid of this. So before I get to that, I want to tell you what an edge contraction is. Now actually, before I tell you what an edge contraction is, I want you to think of multigraphs. So what is a multigraph? A multigraph basically has parallel edges. Okay, multigraph has parallel edges. So this, for example, is a multigraph. So when you think of a simple graph, you just think of one edge. In a multigraph, you can think of there being multiple edges between any 2 vertices, right? And so this you can also model as an edge weight. Right, you might want to think of the weight of these 2 vertices as 4, the weight of this is 1, the weight of these 2 is 0, because there's no edge, this is 2, 1, so on and so forth. So that's a multigraph. The reason I want to talk about multigraphs is because an edge contraction is essentially going to convert graphs into multigraphs. So what is an edge contraction? So what is an edge contraction? Given edge UV, the contraction is obtained by merging U comma V into a single vertex and keeping all other connections, or I should say keeping all other edges. So let me formally explain what this is, and this picture is useful to do that. Or let me start with a different picture. So let's take a graph with 5 vertices, something like that. So if I contract that edge, so let's say this is U and this is V, I'm going to sort of merge these into this one mega vertex, but just keep all the other edges. And this edge will sort of disappear, right? But all the edges will remain. So the contraction will give me this one vertex. Let me just refer to this as U comma V, which I contracted that. And let's say this is 1, 2, and 3. Then the vertex 1 now has 2 edges into that. There's one edge that goes to 3, and there are 2 edges that go to 2. Does that make sense? So I basically just, it's like you should almost think of it, almost like a movie, right? These 2 vertices will bump into each other, they'll become one vertex, and all the other edges just remain. And typically this edge will just discard. So if you start from a graph and you do a contraction, you get a multigraph. But you can do contractions on multigraphs. Now I could contract these 2. Let's say I want to contract this edge, right? So I'm going to contract this edge over there. I'm going to just have one vertex for the agglomerate of u, v, and 2. And then I have 2 edges going here, one edge going to 3, and this is like this new vertex that I created. Yeah?
So we don't add a self edge?
Yeah, so we remove self loops, right? So, so I'll say keep all other edges. We will remove self loops. And depending on the application, in some applications when you actually contract, you remove parallel edges. But for us, we are going to keep parallel edges. So we merge 2 vertices into a single vertex, and we will just keep all other edges, right? So so when you start with a multigraph, you end up with a multigraph. Does that make sense? So that is the process of contraction. Okay? All right. So this is the process of contraction, and so do you all remember what the Mincut is, right? So I'm going to remove all the stuff on that side of the board now. So now I can actually, I can just tell you what Karger's algorithm is. So the Mincut algorithm is simply repeat n-1 times. And repeat the following process n-1 times. Pick, so it's a uniform random edge in the current G. You'll see the G is going to keep getting modified as this goes along. So you're just going to pick a uniform random edge from the graph, right? So you have your graph here, which is a multi-graph, because we're going to do contractions. And so you just pick one of these at random, uniform random edge, UV. Contract UV. Okay, so maybe I should make this n-2 times. So you pick a random edge, you contract it. Then you pick a random edge, you contract it. You just keep doing this. How many vertices are you left with after n-2 iterations? 2 vertices, right? Each time you contract, you decrease by 1. So if you repeat this n-2 times, you will start from your graph and you will end up with 2 vertices and some edges between them, right? Does that make sense? So I'm just going to report that as the cut value. That's the Mincut. That's the algorithm. So report, or I should say output, the number of surviving edges as the Mincut. Just this. So note that every time I contract, I throw away self loops. So after doing all these contractions, I have 2 vertices left. I'm just going to say that's the Mincut. This is the entirety of the algorithm. Like, this is Karger's Mincut algorithm, and we'll analyze. Like, it seems like there's no way something like this could work, right? Especially for those of you who did 102 and you've seen max flow, which is this immensely complicated beast. And this is saying you have to do max flow multiple times. And Karger said, this is it. And so, of course, we'll understand that this has some probability of failure, so we'll have to repeat this entire procedure a bunch of times, but that's the algorithm. Does the algorithm make sense? Do you see why it reports some cut value? Right? Because if you think about what this vertex is, it's a mega vertex that was obtained by contracting something. So let me just draw this picture. So you started with this graph here. The full procedure basically ends up with 2 vertices and a bunch of edges in between. But if you actually go back, then this was obtained by contracting some subset. And this was obtained by contracting the other subset. And so this is exactly the cut value here. Right? So because every time you contract, you basically are just collapsing some subgraph into a single vertex. So does that make sense? Yeah. So the algorithm is really simple. Right? Yeah, I have no, like, you wonder why someone would do something. It seems like this is too trivial to work. So for now, I want you to ignore the technical details of how you would pick a random edge and how you would do the contraction. Like, assume that there's some data structure that you can manage to do that, right? Because we can go back and analyze how long that takes. I just want you to think about what is the likelihood, the probability that this process is actually going to produce the Mincut. So let's define some events. So let's first fix some Mincut. There could be multiple Mincuts, so just fix some Mincut. Okay? So maybe that's the cut S complement. Right? And so what you have is you have S complement, and you've got the edges there. Okay? And I want to say, what is the probability that the process outputs basically this cut value? Or we could even think of, if you actually think of the 2 vertices that remain at the end, this is like a specific set. Right? You can think of this as actually some set of vertices that got contracted to that. And S complement, you could imagine outputting not just the value but the cut itself, like S and S complement. Right? So we could ask, what is the probability that the process actually outputs some specific Mincut SS complement? Does that make sense? So can you think about what does that mean? So every time you're picking a random edge, what is it that you want or do not want to happen when you pick this random edge? So here's the specific cut. Here's a graph, right? Here's some graph. You're picking a random edge and you're going to contract. What is a safe edge to contract? And what is an unsafe edge to contract? Yeah?
The safe edges are all of the ones not in E of S complement.
That are not in this cut. So if you contract any edge here, then you kind of, you preserve the cut, right? No. We should have turned the camera around to catch that, right? Yeah.
Trying to be gentle. Wasn't the answer.
I need to ask more simpler questions now, right? So that more people can have candy. Yeah. So do you see that, like, as you're contracting edges, if you contract any of these edges, then it's fine. You're not going to destroy that min cut. And if the process only contracted edges here and here, eventually it's going to end up with the right answer. Right? If at any point it actually contracts this, then it's gone. Like, it's failed. So the probability that the process outputs S complement can be written as, so okay, but before I put math, let me just say this again. How many edge contractions are you doing? How many? Look at the algorithm. N minus 2. N minus 2, right? So you have these N minus 2 experiments. Each time you pick a random edge, contract. Then you pick another random edge, contract. You keep doing this. And you want to avoid this unknown set. Like, the algorithm doesn't know the set. But the algorithm wants to avoid this set. Right? It seems like the odds are just going to be too small. Okay. So let me write this as the probability of the event E1, E2, up to En minus 2, where Ei is the event. Now, this is a specific event that contracted, or I'll say the random edge of the ith iteration is not a cut edge. Where I'm specifically talking about this cut, right? The S complement cut edge. So you want the probability, so all of these events need to hold, right? At every iteration you have to avoid the cut. And this is just saying that no, these are just all these events. Now note that there is some sort of dependence on these events, right? Because depending on what happens here, it could affect what happens there, so on and so forth. But each of these is like a well-defined event. So do you know what conditional events are? Vaguely, sort of, kind of, right? Okay, so suppose you have two events. A and B. Okay, so always Venn diagram, because this is like the set of, remember we had this sort of set of outcomes. It's a discrete set. So each event is just some subset of outcomes, right? So A is some subset of outcomes. B is some subset of outcomes. So think of these as events. And what is the intersection? It's just that. So we can also write this. This is like the law of conditional probabilities. This is the probability of A happening conditioned on B times the probability of B. Actually, this is like the definition of conditional probability is exactly this divided by this, right? So this is saying that for A and B to happen, first B must happen, then assuming B happens, A must happen, right? So this is saying first this happens, now you've conditioned on B happening, and so A must happen, which puts you in that middle region, right, in the intersection. Right, this is pretty much the definition of conditional probability. This is like the only math that you need to know to analyze this, and how to multiply in, basic arithmetic. Okay, so Does this make sense? This is the law of conditional probabilities. And sort of intuitively, it's just saying that for two events to happen, well, one of them has to happen, and assuming that happens, the other must happen. Right? And that's the conditional probability. Okay? All right. And so now let's go back to this. And we're just going to write this in terms of various conditional probabilities. So first, we're saying what's the probability of the first event times the probability of everything else happening conditioned on the first event. Right? So this is, I'll say, the probability of everything else happening, which is, I'll say, yeah, I is going from 2 to n minus 2. This is all of those events happening conditioned on this event. Okay? And then I'm just going to sort of keep breaking this further and further and further. Say, well, what is this? Well, this can be written as the probability of the second event conditioned on first event times the probability of whatever remains, 1, 3, to n minus 2, conditioned on both the second event and the first event. Right? This is then, this makes sense? So I'm just, if you chain this together, it just says that what's the probability that this happens? Then conditioned on this, what's the probability that this happens? Then conditioned on these two happening, what's the probability a third one happens? Then conditioned on the first three happening, what's the probability the fourth one happens, so on and so forth. Right? So that's really what's going on. And so I just expanded it by one step, but then you can expand it completely. So you'll see that what you're getting is the product of probabilities, where it's the product of the ith event conditioned on the first I minus 1 events. So I'll write down the final formula, and then you tell me if you needs more if this needs more explanation. So let me take it and write it there. Do you guys want to try it on paper first? So why don't you try it and then see if you get the same formula that I did, and that will sort of test whether you got it or not. In the meantime, I'll find a piece of chalk that won't hurt my thumb. Okay. Yeah. So what? Like, I want to write this as a product. I going from a to n minus 2, right? Some product of conditional looking things. What are those conditional things? So I showed you the first one, and I showed you the second one. You break this up further, you'll get the third one. I'll even start, it's the probability of the ith event conditioned on, so you have the answer. Does anyone else? Once you write the first 3 or 4, then you start seeing that there's a pattern.
How long long do you want to have them spend thinking about this? Because one of the things we sometimes do is like break up into small groups to sort of. For that.
I don't know. What do you want to do? Should I just write it down? Huh? Yeah, maybe I'll write it down, and then maybe at the end, if you want to break up and sort of explain, might help. So the thing is, you look at this as the first event happening, the second event conditioned on the first, the third event conditioned on the first two, and so on and so forth. So you condition on j going from 1 to I minus 1 of that. Where conventionally, if you're going from 1 to 0, then you don't have anything, right? So when I is equal to 1, the thing over there is 0, so that means there's nothing here. So this is just saying that it's the probability of the ith event conditioned on the first I minus 1 happening. And because you multiply all of these together, it's like the probability of the first event times the probability of the second conditioned on the first, times the probability of the third conditioned on the first two, so on and so forth. Right? So I've just sort of broken it up in this way so that now we can think about each of these events conditioned on these events. So can you tell me what this means in English? Like, what does all this like Greek gibberish mean? You know what the ith event actually is, right? So given this language, describe this event to me. Someone describe what this is. Yeah? So what yeah, go ahead.
It's like the culmination of picking edges that are not the mincut.
Okay, good. So this means in the first I minus 1 iterations, the edges missed the mincut. They avoided the mincut. And this is the event that in the ith iteration, it avoided the mincut. Which means in the first I minus 1 iterations, the algorithm has succeeded. It's avoided the mincut. And this means that it's avoiding the mincut in the ith iteration. So the probability is, what is the probability that in the ith iteration it's going to avoid the mincut, given that it's avoided the mincut in the first I minus 1 iterations? Right? That's what it means in English. So I'm going to sort of remove this. And this is just saying that this is the product from I going to 1 to n minus 2. The probability of the ith iteration avoiding the mincut. You understand what this means, right? The edge that you pick is not from the mincut. Conditioned on, given that the first I minus 1 iterations avoided the mincut. Like, that's what this is saying, right? So just saying that what is the probability that the ith edge that is picked, or the ith iteration, which is somewhat, it's basically the ith edge that is picked, has avoided the mincut, given that the first I minus 1 iterations or edges picked have avoided the mincut. That's what this is, right? That's what this thing in Greek really means. Okay? All right, so now let us go back to here. I want to keep the mincut algorithm, but I can remove this. Okay? So let's just say, suppose the mincut value is k, right? So if you look at, and we want to understand this event, the probability of the ith event conditioned on the first I minus 1. What this means is essentially the Mincut stays at k, right? Because you always avoid picking the Mincut, so the Mincut is not going to go up. If you destroy the Mincut value could go up. But this means that the Mincut value is going to stay at k. Okay? All right, so let's just try to bound this. What is the probability in the very first step of avoiding the Mincut? So let me remind you, here's the Mincut. How many edges are there? There are k. You're picking one at random. Picking one edge at random. How many edges, yeah?
Would it be, oh god, 1 over k?
It's not 1 over k. So what is your sort of operation? You're basically, you're picking a random edge and you want to miss this. Yeah? No. Someone had their hand up. Yes?
M minus k over m.
M minus k over m. Good. So there are m edges in the graph. Right? So this is m minus k divided by m. Right? So nothing that surprising yet. Or I can write this as 1 minus k over m. But then the problem is you need to know how many edges there are. Yeah, that's why I put something in the box over there. And I sort of conveniently left that up in a corner. Okay, so how many edges are there in the graph, right? Okay, so do you guys know this formula? It's also, I think, is referred to as the handshake lemma. The number of edges in the graph is basically, or if you sum up all the degrees, you get twice the number of edges. Right? So if you look at all vertices in V and you sum up the degree of V, then you get twice the number of edges because every edge is counted twice. Right? Every edge contributes to 2 degrees. My degree and the other person, right? Right? So this is called the handshake lemma. So what it says is that the number of twice the number of edges, or the sum of degrees is twice the number of edges. But you have this thing over here, this formula here. Yeah, this needs to be turned to that. That the degree is always at least the Mincut. Right? So let's just plug that thing over there. Okay, so the degree is always at least the Mincut. How many vertices are there? Let's say it's n times k. Right? So, in other words, m to m is at least n times k. Right? Or alternately, k divided by m is at most 2 divided by n. Right? I'm just moving things around. So at this point, actually, we don't even need probability. All we need is some arithmetic. Right? So I'm just saying k divided by m is at most 2 divided by n. And if you saw what I have as the probability is 1 minus k over m. So I'm saying this thing is actually really small, which means this thing is really big. And so actually what I get here is removing that. This is 1 minus 2 divided by n. Right? It's like it's a magic trick. Right? So the probability, actually your odds are pretty good. This is the probability that you're avoiding the min cut at the first step. Okay? So now we need to say what happens in the next step. But in some sense, if you think about it, the same logic is going to hold, because the min cut value is still the same. There's only one difference when you look at the next step, conditioned on the fact that if this happens, you know the min cut is going to stay as k. So what is the difference between the first iteration and the second iteration? Yeah?
The number of edges goes down.
The number of edges has gone down, but with respect to this formula, what else has gone? But okay, so the problem with the number of edges is you don't know by how much it's gone down. Right? It's a little.
So the number of vertices.
The number of vertices has gone down by what? By how much? In one iteration? By 1. By 1, right? So in the second iteration, you have n minus 1 vertices, and you have the same logic. You have the same logic here. Does that make sense? So I'm going to remove all of this. Hopefully you understand all of this by now. I want to keep that piece of math there because that's sort of where the magic has happened. So what have I said? I've said the probability of this is at least 1 minus 2 over n. Right? The probability of this conditioned on that. So when I condition on this, I know that the min cut value is still k. The only difference is now there are n minus 1 vertices. So I apply the same logic. I get 1 minus 2 divided by n minus 1. To the third time, I get 1 minus 2 divided by n minus 2. So on and so forth. So if I do this, one minus 2 divided by n minus 2. If you're looking at what is going to happen at the ith, right, so in the first iteration there are n vertices, in the second there's n minus 1, in the third it's n minus 2, so you'll get n minus I plus 1, right? That's the pattern, right? Because when I is equal to 1, maybe I should have started it from 0 at the, but you know, it's the same logic, off by 1 error. And all you need to do now is to multiply all of these together, right? And then you get a lower bound on the probability. Does that make sense? So this is what happened in the first iteration. The second, this is like it's just completely magical that you'd be even able to analyze this and get some reasonable bounds on the probability. But now you're going to say, okay, but how am I going to multiply all of these? And then we'll come to the next magic trick. Okay, so the probability that a min cut is output is at least the probability of 1 minus 2 divided by n minus I plus 1, where I is going from 1 up to n minus 2. Yes. Okay? So this looks somewhat daunting, but let's just write out each of these. So what is this? I could write this just as n minus 2 divided by n. So it's n minus 2 divided by n. And what is this? N minus 3 divided by n minus 1. Divided by n minus 1. What's the next one? What's the next one? Yeah?
N minus 4 divided by n.
N minus 4 divided by n minus 2 times n minus 5 n minus 3 goes all the way up to what? What's the last term? No, yeah, so what do I get there? What do I get there?
0.
No. So let's plug in n minus 2 over there, right? 1 minus 2 divided by n minus 2 plus 1, 1/3. Right? Do you see stuff canceling out? That cancels out with that, that cancels out with that, that cancels out with that. Canceling, canceling, that will cancel out with the 3. You have a 2 left over here. This is 2 divided by n times n minus 1. Right? So that's the probability. So the probability that the Mincut is output is effectively, it's actually 1 divided by n choose 2. Right? So, and that's optimal actually. That's like that. So it's basically omega 1 divided by n squared. So the probability that this crazy procedure actually outputs the Mincut is 1 divided by n squared. So what you do is you simply repeat this procedure n squared times, take the minimum of what you got, and you have a Mincut with high probability. Right? So you can, no, I'll work that out in a second. But first, make sure that you see this. Right? It's like complete black magic.
Wait,
Yeah?
so that probability is the probability that the Mincut is the output?
Yes. So it's a small probability.
Yeah, I was gonna say.
But you can okay, good. So this is a small probability, but you know that with 1 over n squared probability, you'll get the Mincut. So you repeat that procedure n squared times.
And one of them is gonna be.
One of them is going to be the Mincut.
And then how do you find out which one is the Mincut?
You output the minimum of what you got.
Oh, okay.
Because every time you get a cut.
Oh, it's because it's a number.
Yeah, it's a number. So you just output the smallest number that you get. So you repeat, I'll write that down shortly, but you repeat this n squared times and output the minimum of what you got. And that's Karger's Mincut basically. It's like, it's surprisingly short. I mean, this was a research paper maybe 30 years ago, 40 years ago. So it's not that old. Right. Well, depending on how old you are, I guess. But that's the algorithm, right? So it just says you repeat the contraction procedure n minus 2 times. The probability that you actually found the Mincut is omega 1 over n squared. Because of this sort of amazing telescoping product, right? You just sort of everything just cancels out. You get 1 over n squared. Yeah?
Can you explain why, like, if you run it again for n squared times, it's guaranteed?
Yeah, so I'll do that. Yeah, I'll do that.
One question.
Yes.
So this isn't really like that good for massive graphs, is it?
It's a good point. So the thing is, it'll be n. We'll see that it's n squared times. So you have to do some data structures updates to maintain all that. And if you look at what one run costs, it's n squared. So it's n squared times n squared, just n to the 4th. But Karger had an even more clever trick. So what he does is, instead of contracting all the way down to 2, he says you contract down, this is crazy, so you contract down to 2 graphs with n over root 2 vertices each, and then you repeat independently recursively on that, and you work it all out, and it's n squared. Right? So yeah, it's and n squared, if you think of the fact that the graph is dense, that there are n square edges in it, that's the best you can do. Because that's what it takes just to read the graph. And typically Mincut is when the graph is dense. So in that case, it's optimal. It's like, up to some small factors. If the graph has less than n square edges, then it becomes a little trickier. But But the point is, if you wanted to get the same n to the 4th running time with a deterministic algorithm, you would end up doing like about 1 week worth of max flows like, and all of this complicated stuff. But yeah, I'll do that other part. But is this clear? I mean, it's unfortunately the problem with this is even now I stared and like, wait, what? Right? So it looks like it's clear, but it's it's a surprising statement. So the probability of the Mincut is actually, let's even write down the exact expression, right? Is at least 2 divided by n squared. That's the probability. Okay. So at this point, what is done in randomized algorithms is a trick that's called boosting. So the boosting idea is, so I'll just say repeat n squared over 2 times run Karger's Mincut algorithm, and then over here output the smallest cut seen. Okay? So what is the probability that this is not going to output the max cut? What is the probability that this process is not going to output the max cut? So what is the probability that this is not going to output the max cut? 1 minus 2 over n squared. That's the probability that this one doesn't, each individual run. But you did n squared over 2 runs, and I chose this to be the reciprocal of that. Okay, so at this point it's an elementary probability calculation. So what's the probability that all of these iterations failed? What is it? What's the expression? So there's one, it's like a coin, right? You flip a coin. And with probability 1 over 2n squared, you fail. So you fail with really high probability. So you flip the coin again. You flip it again. You flip it again. They're independent trials, right? And how many independent trials have you done? That many. Right? So the probability of not getting the Mincut, not getting the Mincut, is basically you have to fail in every single trial. You have to fail every single trial. Do you know what this thing is? Sort of as n goes to infinity, what is this? May or may not have seen this. Yeah?
E.
Good. But 1 over e. Oh. Right? Because it's something smaller than 1, right? It's like, so this is actually less than 1 over e. Okay? So it's 1 divided by 2.7. Okay? So you might say, well, okay, that's okay, fine. So now I get it with some probability. But you might say, I really want to get the Mincut with really small probability. Right? Really small probability. So let me multiply this by 10. Times. So let's go back here. This times 10. 1 divided by e to the power 10. Right? That's much smaller than 1 divided by 1,000. Now your odds don't look that bad. The probability of not getting the Mincut is less than 1 over 1,000. And actually the boosting is really cheap. suppose you wanted 1 divided by 1,000,000, you make that 90. You put a 90 over there. Actually, you don't even need 90. I think 30 should do the trick, right? 30, 30, right? And, or, yeah.
Because he's greater than
Yeah, so you get 1 over e to the 3 to the power 10, and it becomes much, much smaller, right? Like e to the 3 is definitely more than 10, so you get, that's like less than a billion basically, right? So the odds of not getting it is probably less than the probability that your code has a bug in it or that your hardware failed, right? I mean, boosting is really cheap. Because it's like you put it in the exponent, the number of trials. So if you double the number of trials, you actually square the error probability, right? And so you repeat basically this n square times. That's the algorithm. So in terms of runtime, it turns out to be something like O of n to the 4th, because each run of Karger's Mincut is going to be like n squared. And then there's a way of getting it down to from O of n to the 4 to n squared, basically using these ideas and some of the stuff with recurrences. But it's not impossible. Like that would be maybe another like half an hour to 45 minutes of lecturing. It's not like absolutely crazy. But the point is, the algorithm is so simple. And that sort of happens over and over in randomized algorithms, that the algorithm will just be deceptively simple. The analysis will be tricky and involve lots of tricks. But the analysis is, the algorithm is both simple, it'll be easy to code, it's easy to describe. And this is one of the reasons why people study randomized algorithms. So any questions? Does this make sense, the boosting part? It's basically like each trial is like flipping a coin. And so you have this extremely, it's like gambling. You have it's the opposite of gambling actually, because your odds are actually going to improve. But the idea is each trial has a very small probability of success. But if you repeat it enough times, you're going to see success at some point. And because every time this process returns a cut, it returns a genuine cut. It's just not the min cut. So you can just output the minimum that you've seen so far. And that's it. And so the key is, it's sort of written both statements above. One is that the min cut is always less than the degree. And so we use this fact to prove that the probability that the min cut is output is at least 2 over n squared. And then that's it, right? So this part that I did over here, the boosting, this is considered routine. This is like routine calculation. The magic is actually in proving this bound. Because often what you need in these cases is to just get some non-trivial odds of getting the right answer, and then you repeat it enough times to sort of get the final answer. Okay? Questions? Yeah.
Why did you choose n squared over 2 for the number of times you repeat?
So what I wanted to get is I wanted to get this thing to be 1 over e. So if I simply put whatever is the reciprocal of what's here, I get 1 over e. That's like I get something like a half. And then I can just repeat that as many times. That's for ease of calculation. Another way of thinking of this is, here's maybe an easier way. So you have this process, and the odds of you winning, which is actually getting the right answer, is this, 2 over n squared. So let's say the odds of winning is p. Ask you, how many times do you need to play this game to win at least once? It's like 1 over p seems like the right thing, right? It's also, you can also do it through linearity of expectation, but it's like saying that if the odds of winning is p, like each time you flip a coin, it comes heads with probability p. How many times do I have to flip the coin to see heads? 1 over p times will give you some reasonable odds. All right, any other questions? Yeah?
Explain how that collapses to 1 over e.
How this collapses? So let me again complain about your calculus education. Sorry. No. So the way to write this is, so let's just say that this is x, and I have this, right? It's 1 minus x to the power 1 over x. And if you take the limit as x goes to 0, this thing will give you 1 over e. This you may have seen at some point, right? So it's just the same logic. The idea is that n is so large that you're sort of approximately at the limit. If you want to do it formally,
Maybe x goes to infinity instead of x goes to 0.
x goes to 0 because this is going to 0. So another way of looking at this is actually there is a simple upper bound of that form. Like 1 minus x is at most e to the minus x. So you can plug that in as well. Right, so 1 minus, so this is what? 1 minus x plus x squared divided by 2 factorial minus x cubed divided by 3 factorial, so on and so forth. So the point is that this part is going to be positive, sort of like, well, I should say, x is less than 1, right? And in our cases, this is less than 1. So this is going to be more than this. So the positive is going to be more than the negative. So all of this stuff is positive, and therefore e to the minus x is more than 1 minus x. So you can plug that bound in over here. But usually the quickest sort of calculus way of reasoning about this is to say that this limit is 1 over e. But it's the same argument here, yeah. Yeah, so this is often one of the reasons why in a lot of these analyses you'll see e popping up over and over again, because you see these sorts of calculations. Yeah. It's interesting, another way of thinking about what does e really mean, like where is a crazy number like e going to appear in my life? It's really about flipping coins. Like I have a coin, right? And the odds of success is p, where p is something really small. So I'm going to flip the coin 1 over p times. What is the probability I see a heads? It's actually like 1 over e, right? So it's like this very simple discrete process that you can think about, which is actually related to this bizarre transcendental number. Yeah? All right, I think we should end here. I can take more questions after the